Look at this sentence, frozen mid-thought. One word is glowing, the little word it. Watch what it does. It reaches backward, throwing arrows to every word that came before it. But the arrows are not all the same. One of them is thick and bright, aimed straight at a particular noun earlier in the sentence. The others are thin, almost faded. The word it has decided somehow what it refers to. This is attention. It is the mechanism that lets a language model figure out that it means the animal and not the street. And the remarkable thing is that nobody told the model this rule. It learned to draw these arrows on its own. Over the next few minutes, we are going to build this machine from scratch. We will see what those arrows really are, where their thickness comes from, and why this one idea reshaped the whole field of artificial intelligence. Let's start by shrinking down to a single word. Inside the model, a word is not a word. It is a vector, a long list of numbers, a point floating in a high-dimensional space. We will draw it as a small stack of numbers, but picture it as an arrow pointing somewhere in a space with hundreds of directions. Now here is the central problem. This word vector, sitting by itself, has no idea what surrounds it. The word it looks identical whether it refers to an animal or a street. Meaning does not live in single words. It lives in relationships between them. So we need a way for words to talk to each other, to pass information along. Each word should be able to look around, decide which other words matter to it, and pull in a little of their meaning. That looking around, that selective gathering, is exactly what attention does. To do this, each word is going to play 3 roles at once. From its single vector, the model produces 3 new vectors. We will call them the query, the key, and the value. Think of them as 3 colored shadows cast by the same word. Each of these 3 comes from multiplying the word vector by its own matrix of learned numbers. 3 matrices, 3 projections. During training, the model tunes these matrices until the shadows point in genuinely useful directions. For now, just hold on to the picture. Every word becomes a query, a key, and a value. Let me give you an intuition for what these roles mean, because the names are borrowed from something familiar: searching. Imagine you walk up to a library help desk with a question in mind. That question is your query. Every book on the shelf has a little label on its spine describing what it is about. Those labels are the keys. You compare your question against each label to see which books are relevant. The better a label matches your question, the more that book lights up. And inside each book is its actual content, the information you would take away if you opened it. That content is the value. So the query asks, the keys advertise, and the values deliver. Attention is just a soft, weighted version of this search. Now back to the mathematics, carrying that picture with us. The word doing the looking, our glowing it, uses its query vector. Every other word, including it itself, offers up its key vector. We are about to compare one query against all the keys. How do we measure whether a query matches a key? With a dot product. We line the 2 vectors up, multiply them component by component, and add it all up. The dot product is large and positive when the vectors point the same way, and small when they point in different directions. So the dot product is a similarity meter. A high score means this key is exactly the kind of thing my query was looking for. A low score means barely relevant. This single number is the raw ingredient of that arrow's thickness from the opening scene. Now we do this for every word. The query of it dot products against the key of the first word, then the second, then the third, all the way across the sentence. Each comparison spits out one number. We collect them into a row. This row of raw scores is the first draft of attention. Notice that the number sitting under the referent noun is large because the model learned to make that query and that key point in similar directions. But these raw numbers are unruly. Some are big, some negative, and they do not add up to anything meaningful. Before we go further, there is a small but important adjustment. When the vectors are long, these dot products can grow uncomfortably large, which makes the next step behave badly. So we divide every score by the same fixed number, the square root of the vector's length. It is a gentle rescaling that keeps things stable. Now the key move. We want to turn this row of scores into a set of weights, real percentages. that describe how much attention to pay to each word. Those weights must all be positive and must add up to exactly 1. For that we use a function called softmax. Softmax does two things. First, it exponentiates every score, which makes them all positive and dramatically exaggerates the differences, so a slightly higher score becomes a much larger number. Then it divides each by the total so the whole set sums to 1. Big scores become confident weights, small scores nearly vanish. And there it is, a probability bar. Each segment is how much our word it will attend to each other word. One tall segment sits over the referent noun, and thin slivers cover everything else. This bar is literally the thickness of those arrows we opened with. Take a breath, because this is the heart of the whole idea. We asked a question with a query, matched it against every key, and softened the answers into a clean distribution of attention. The model has decided for this one word where to look. Now we need to actually use that decision. Remember the third role, the value vector. Every word carried a value, the content it offers up. We are going to blend those values together, but not equally. Each word's value gets multiplied by its attention weight from the bar. The word we attend to strongly contributes most of its value. The words we barely attend to contribute almost nothing. We add all these scaled values together into one new vector. That sum is the output of attention for the word it. Think about what just happened. The word it started as a lonely vector that did not know what it referred to. It leaves this process carrying a large dose of the referent noun's meaning mixed in. Information has flowed from one word into another. The word now understands its context. Let me replay the whole pipeline for one word in a single sweep, so the shape of it settles in. Query out, dot product against every key. Scale, softmax into weights, blend the values. Out comes a context-aware vector, that is one attention computation start to finish. But it is not special. Every single word in the sentence does this at the same time. Every word forms its own query and goes looking. So the noun asks its own question, the verb asks its own question, and each ends up attending to a different mixture of neighbors. Because every word queries against every word, we get a full grid of scores. One axis lists the words doing the looking. The other axis lists the words being looked at. Every cell holds one attention weight. This grid is the attention matrix. Let's make it visual by coloring each cell by its weight. Bright cells mean strong attention. Dark cells mean the model is ignoring that pair. Now the matrix becomes a heat map, a portrait of who is paying attention to whom across the entire sentence. Read across the row for the word it, and you will see one cell blazing over the referent noun, just as our arrows promised. Each row of this heat map is one word's probability bar, and because it came from softmax, every row still sums to 1. This is also why attention is so powerful compared to older approaches. Earlier models read a sentence word by word, passing a running summary forward, and distant words easily faded from memory. Here, any word can look directly at any other word, no matter how far apart, in a single step. And because there is no left-to-right chain, every one of these comparisons can happen at the same time, in parallel. The entire attention matrix is computed in one big burst of matrix multiplication. This parallelism is a large part of why these models can be trained at enormous scale. Now, one attention matrix captures one kind of relationship. But language has many kinds of relationships at once. What does this word refer to? What is the subject of this verb? What tense are we in? A single grid cannot track all of these cleanly. So the transformer does not use just one attention. It runs several in parallel, side by side. Each one is called a head, and each head gets its own separate query, key, and value matrices. That means each head learns to ask a different kind of question. Watch what the heads specialize in. One head might learn to connect pronouns to the nouns they refer to. Another might link each verb to its subject. Another might just attend to the immediately neighboring word. Different heads, different heat maps, different jobs. Nobody hand-assigned these jobs. We never told head 2 to track subjects and verbs. The model discovered this division of labor on its own, simply because splitting the work this way helped it predict text better during training. Structure emerged from optimization. Each head produces its own blended output vector for every word. To combine them, we simply stitch the heads' outputs together side by side and pass them through one more learned matrix that mixes them into a single result. Many perspectives folded back into one vector per word. This whole assembly, the queries, keys, values, the softmax, the many heads, has a name: multi-head self-attention. Self, because the words are attending to each other within the same sentence. It is the fundamental building block of the transformer, and a transformer is mostly this block repeated. The context-enriched vectors flow into another attention layer, and another, stacked many times deep. With each layer, the words gather more context, and the relationships the model can represent grow richer and more abstract. There is one subtlety worth naming. Attention by itself treats a sentence as an unordered bag of words. The dot products do not know which word came first. So the model adds a small positional signal to each word vector at the start, quietly encoding order into the numbers. Now step back and recall the paper that launched all of this. Its title was a bold claim: attention is all you need. Before it, the best language models leaned on that slow, sequential, word-by-word machinery. The authors proposed throwing it out entirely. Their bet was that this mechanism, on its own, could carry all the heavy lifting of understanding how words relate. No recurrence, no reading strictly left to right. Just let every word look at every other word directly in parallel, layer after layer, and it worked spectacularly. This is the engine underneath the language models you have heard about. Every time one of them writes a coherent paragraph, it is running billions of these dot products, softmaxes, and weighted blends, letting context flow between tokens across dozens of layers and many heads. So let's return to where we began. The word it, glowing, throwing arrows back through the sentence. You now know exactly what those arrows are. They are softmax weights, born from a query meeting a set of keys, deciding how much of each word's value to pull in. The thick arrow to the referent noun is a large attention weight. The thin arrows are small ones, and the meaning that flows along them is the blend of value vectors. That single elegant idea, letting words decide what to look at, is how attention actually works. From here, the same machine that resolves a pronoun also tracks grammar, follows arguments, and stitches together long documents, all with queries, keys, and values. Once you see attention as a soft search that every word runs at once, the modern transformer stops being a black box and starts making sense. If this made it click, subscribe for more visual math.